Welcome to this evening's webinar on behalf of Learnus. My name is Richard Newton-Chance and I'm Chair of Learnus Council. Learnus is dedicated to connecting educators and world-leading scientists who specialize in the study of the brain, the mind, and behavior in order to use the evidence and insights from high-quality research in these multidisciplinary fields to improve and enrich teaching and learning for all. I'm delighted to welcome Professor Denis Mareschal to this evening's webinar. Professor Mareschal is Director of the Centre for Brain and Cognitive Development at Birkbeck University of London and a founding member of the Centre for Educational Neuroscience.
Thank you very much, Richard, and thank you all for coming. I'm bowled over by the impressive curriculum vitae that you've read out. It's kind of putting me off my own presentation. But let's give it a go. Okay, so today's, actually, let me just have one person. There we are. So today's webinar lecture is called Unleashing the Toddlers, Lessons from the New Birkbeck ToddlerLabs. It kind of makes it sound like the toddlers are so dangerous they should be tied up. But that's not at all the idea. The idea here is that children really need to be allowed to explore the world naturally if we want to understand how they learn under natural circumstances. So, oops, let's see. Oh, yeah, there we go, that works. This is not the first time that Learnus has visited the Toddler Lab. A couple of years ago, there was a short film made in which several of the researchers presented their work. I was asked to answer many questions about the basic foundations of the Toddler Lab, and I direct you to this Learnus film about that if you're interested in more of the background. What we're going to do here is maybe give you an update of what's been happening since then. So it's important to understand that the Toddler Lab is one of the constituent elements of the Center for Brain and Cognitive Development. So the Center for Brain and Cognitive Development is about 25 years old, and it has a number of constituent labs. The precursor to the Toddler Lab was the Baby Lab, which was founded in 1998. So the Baby Lab's mission was to study the relationship between brain and behavioral development in under 2-year-olds. And that's one way of doing that was to use neuroimaging technology such as EEG, which measures the electrical activity in the brain, and functional near-infrared spectroscopy that measures the kind of brain oxygenation in various parts of the brain. But the technologies that existed 20 years ago required these systems to be plugged into really big amplifiers. So you can see in the two pictures at the bottom, babies wearing a kind of hairnet that measures electrical activity and a kind of old-fashioned functional near-infrared spectroscopy system that measures brain oxygenation. And what you don't see is that all of these little sensors are actually connected to wires which are plugged into an amplifier. So that means the child can't really move very far. And that's okay if you're studying babies, because most babies, such as the one up here, will happily sit and watch interesting and exciting events. But as soon as you want, or if you're interested in kind of studying mobile children that are maybe 18 months or 24 months or older, this is not a satisfactory way of studying their behavior for two reasons. One is they get frustrated. They just pull the caps off, and there you are, you've lost 5,000 pounds. And the other thing is because their natural behavior is to move around. 2-year-olds will move around to explore the world, not just sit there watching things. So the future, 8 years ago, was to construct and design a new lab, the Toddler Lab. And the Toddler Lab, as we'll see, was really designed to try to overcome those problems, to use wireless technologies. So the children didn't need to be plugged into a wall, into an amplifier to study their brain function. They could move around, and also to create labs that resembled as much as possible real-world context that the children would be evolving in. But it's no longer the future, it is the present, of course. The Toddler Lab has been open for about 4 years now. And so we've had a chance to start projects, and we're really in full swing as it is. So what I'm going to do today, as I mentioned, is to really give you an update on a selection of the ongoing work, to give you a flavor for the kinds of things we're doing, the kinds of methods we can use, and the kinds of questions we might be asking. There won't be that many results because these are projects that are still ongoing. So just to remind everyone, what we have as research tools in the Toddler Lab, beyond the usual kind of behavioral setups that allow us to see, play with children, see what they understand, how they learn, and so forth, are wearable neuroimaging technologies. So these take the form of little caps, like swimming caps, and sometimes they're like helmets, in which there are sensors. Here, this is electrical, and wearable EEG system. So these sensors are non-invasive, and they basically record the electrical activity at the surface of the scalp. And all these wires, rather than being plugged into a wall, go into a little emitter in the backpack that the little girl is wearing. And that then transmits to a receiver somewhere else. And that means that the child can run around, as we see on the right here. A child can run around and play realistic types of games, and importantly, interact socially in realistic ways. So we can start to understand how their learning is scaffolded, for example, by social interactions with other people, and how this is manifested in their brain activation. And when they become ready from a neural perspective to, say, understand another person's perspective, and so forth. We also have head-mounted eye trackers. So on the right here is on the left, sorry, here is an example of a young man wearing a head-mounted eye tracker. So the eye trackers, what this does is it's a little camera at the end, and it's looking at the children's pupils. And from the angle of the pupils, it's able to calculate exactly where in 3D space the child is looking. So this means that when we're measuring their brain activity, we know what they're actually looking at instead of guessing what they're looking at. So you might think they're looking at mummy when you're recording the brain activity, but maybe they're looking past mummy at the wall behind them. With the eye trackers, we know exactly what they're looking at. And finally, the other method that you'll see throughout all the labs here is what's called optical motion tracking. So movement actually is a window onto the mind. Movement betrays our unconscious or even conscious but unexpressed intentions, beliefs, and desires. So if you, for example, ask someone to reach for a mug, I've got a mug here, ask someone to reach for a mug on their desk, but next to the mug, you put something really attractive, like a nice ice cream cone, and you measure the trajectory of their reach in detail. Even if they're not reaching towards the ice cream cone, they're ignoring it completely, their movement is slightly deviated in that direction because part of their mind is going, ooh, I would love that ice cream cone. So we can measure these kinds of deviations in non-directly perceivable deviations in movement that tell us the kind of competing thoughts and desires within the child's brain using optical motion tracking. And the way that works is that there are in this picture on the right, you can see a little circle at the top, and the circle is actually emitting, it's a camera that emits infrared light, and the child is wearing some reflective markers, the little balls you see on her arm, and those balls reflect the infrared light. It gets picked up by the camera, and again, this allows us to measure very, very accurately the kind of coordinates, the movement of the child. So we have neuroimaging, wireless neuroimaging technique methods. We have wearable eye tracking, and we have motion tracking. And we can put all of this stuff on the child at the same time and get a really rich sense of what is happening in their body and in their, in their brains when they're interacting in these kind of natural social interactions. So in addition, we have, as I said, in the Toddler Lab, each floor is designed to look like a natural environment. So we have the home lab, for example, which is meant to look a little bit like, or not a little bit, to look like various home environments with a television screen, tables, and various things like that. We have a preschool early education environment. So the preschool lab is designed to look like a typical nursery or preschool environment with a kind of play corner and Lego corner and so forth. And I'll tell you much more about that later in the talk. We have a nap lab where we can study the brain activity of the child while they sleep. So you may think that nothing's happening during sleep, but actually sleep is incredibly important for brain development and for learning. While we're sleeping, the brain is actually processing the information we've acquired during the day, replaying experiences from during the day and kind of separating the wheat from the chaff, deciding which memories, which bits of information need to be laid down for long-term retention and which could just be, thrown away because they were irrelevant bits of information. So this particularly happens during REM sleep, the period of time when we are dreaming. And so we can kind of measure while the child is sleeping, the neural states in their brain and see how this correlates with their kind of subsequent learning. And finally, in the basement, we have what's called the cave, and the cave is actually a virtual reality immersive environment. So this is a 3D environment in which we can transport through technology children to any kind of environments. We could transport them to a virtual playground, a virtual classroom, a virtual farm, and so forth, to again try to explore their interactions, their learning in more naturalistic environments. So I'm now going to step through a number of different examples of studies that are ongoing, and each of these is based in one of those different homeroom environments. As I said, these are ongoing, so we don't really have results from many of them. It's more to give you a flavor for the kind of work that we're doing. So the first one I want to talk about is a series of studies really, but a study run by my colleague, Professor Natasha Kirkham, who's really interested in the impact of noise on learning and attention across early development. So particularly people who live in the city were surrounded by noise. Or if you live in a crowded household, you might have siblings, bickering in the background while you're trying to do your homework, or you've got the television on. And it's really important to understand the extent to which this impacts negatively on learning, especially in young children, maybe before they even go to into formal schooling. They're learning numbers naturally, or vocabulary naturally with their parents, but if there's a television in the background, is that interfering? Or perhaps children from very noisy and more chaotic home environments have developed resilience to this sort of background interference. So to do this, Natasha and her colleague Julia Serino have a series of studies which are in the home lab. So the home lab on the left here, you've got a picture of the setup they're using in the home lab, and it's got speakers dotted throughout the room, and those allow the experimenter to play different levels of sound, but sounds that can move back and forth, so in a natural way. So, for example, the child can be sitting on the sofa or watching a program on television when we can create the sound of an ambulance that would kind of run from the front to the back of the room as well. You might notice at the top here are a series of black dots, which are infrared cameras. So these cameras are there as part of an optical motion tracking system. They're there to kind of measure very accurately the movement of the child, as I mentioned previously. And there we are. Yeah, the optical cameras are in the red boxes here. And so for this particular study, the experimenters, Julia and Natasha, were interested in just the implicit impact of environmental noise on children's attention. So they had children engage in an attention-grabbing task. In this case, it was coloring in a series of animals. But to measure the level of distraction, they got the children to wear these little funny swim caps, neoprene caps, with the kind of reflective markers on it, so that they could measure very accurately how much the presence of a sound or not was actually impacting on the child and causing them to kind of shift their attention a little bit, but shifting maybe their head a little bit to try to find the source of this sound. This is an example of a child who's engaged in the kind of coloring task, and then at random moments, certain distractor sounds will come by. So I will play these. I hope it works. It should work. It's just to give you a sense of what happens. So that was that's not in my background. That was actually a sound that was heard by the children, and of course you can't quite hear it, but it moved from the left to the right speaker. So you have the sound that's moving in the same way that in the home lab the sound would be moving from the front to the back. So that's an aversive but familiar sound. They might have attractive sounds like ice cream, van, or bizarre sounds for someone living in the city, such as a horse. And so, as I was saying, they tested children. They're looking at children from 3 to 6 years of age, so before they get into school, and then after they've reached year 2, to look at how resilient they are to these kind of environmental sounds. And on the right here, there are no actual results. As I was saying, on the right here, we have an example of what they're doing. So they're using the kind of the number of degrees that the child is turning their head as a measure of how distracted are. So on the y-axis, you've got the turning of the head. The more they turn their head, the higher the curve is. And along the x-axis down here is the time, and the different colored lines are different types of distractor sounds. And then they correlate these things with the child's performance on the task, how able they were to sustain their attention, or how able they were to learn a new series of spellings and things like that. Okay, so that's one example of a family of studies that's going on at the moment. Another example is in our NAP lab. So here's NAP lab, and this is some studies run by Dr. Louisa Gosset and Professor Emily Jones. And it's, as I was saying, it's kind of looking at consolidated learning, or how learning is consolidated during sleep. So we know this exists in adults. So if you disrupt sleep, you disrupt learning. And there's an interesting applied dimension to this in terms of special educational needs, because many developmental disorders also have disrupted sleep. And children with some of those developmental disorders show learning disabilities or delayed learning. And no one is claiming that all of the delayed learning is because of the disrupted sleep, but that might be a part of why their learning is delayed. And if there is a clear link between the learning disruption and the subsequent learning, the sleep disruption and the subsequent learning, then sleep is actually something that we can intervene on. By improving sleep quality, we could perhaps improve the kind of learning outcomes of some of these children with developmental disabilities. So how does this work? Again, we need to understand what is happening in the child's brain while they are sleeping. So we get toddlers, preschoolers and toddlers and babies to come in, and we are able to record both electrical activity and blood oxygenation with these kind of caps, as I said, which in this case have a combination of the EEG, the electrical sensors, and the FNIRS blood oxygenation sensors. The child goes to sleep, hopefully, and then we record their brain activity. We can record what kind of sleep state they are in based on the quality or the nature of the kind of EEG recordings during the sleep. So a typical study might involve teaching the child something, perhaps teaching them some kind of association between a cue and a reward in a kind of eye tracking task. And then once they've learned this association, encouraging them to have a nap, either in a push chair or in our nap lab crib, or even on the parents. And we record their brain activity during the nap time. And then following the nap, we do a kind of retention or relearning type task, where we see how much of the rewarding associations they've remembered, whether it's better or that they remember them better or retrieve them more easily after the naps than the equivalent infants who have not had a nap. And then, so we already know that sleep improves retention, but it's trying to identify what elements of brain activity during sleep is the critical element for improving learning. Okay, so just moving on. The third kind of, I'm going to talk about 4 of these. The third kind of work that we've got going on in the third lab, and this is in the K Virtual Reality Lab, is some work done by Dr. Chiara Bulgarelli. And she is kind of looking at the emergence of empathy in kind of the preschool years. So learning to care. And, what exactly is empathy? There are many definitions, but one of them is to say that empathy is really sharing and understanding someone else's emotions. And we know quite a bit about empathy in adults and older children, and how empathy might break down with certain developmental disorders. But we don't really know very much about its early development. And that's because it's not clear when to study empathy. When does empathy begin to emerge? And one thing that's for certain is empathy is a social interaction. So it requires children to experience interactions with others. Could be siblings, as in the picture on the left here, or it could be when they go to start going to play groups or preschool, and then they suddenly are faced with this diverse range of strong emotions from other children, which may be different from them, and having to understand where this comes from and how they should respond and so forth. So the preschool years, 3 to 5, is a good age to start to investigate the mechanisms of empathy development. Because it's actually an age at which many of the children begin to, or at least most of them have kind of left the family household and gone into a larger circle of social interactions through kind of nursery or reception at school. Now, how do you study empathy? Well, empathy in adults is often studied by getting adults to watch videos or to read clips, and then to kind of try to explain the emotional experiences that the characters in the clips or in the scenarios are experiencing and what they would do. But this is just not possible with young preschoolers. And it's because A, they don't comply, and B, because it's kind of very challenging to elicit obvious empathy type responses from static pictures and artificial scenarios in these children. So again, fantastically, we can use this kind of novel developments, technological developments of wearable technologies, and the kind of natural environments that we have in the toddler lab to set up natural scenarios in which the child would be required to, or yes, to kind of demonstrate some kind of, or expected to experience some kind of empathetic response. And we can then kind of record brain activity during these responses, and maybe to try to understand the associations between what kind of neural responses need to be in place before the child can demonstrate overt empathetic responses and so forth. So in this case, what Chiara has started doing is to use the virtual reality environment in the basement, the cave. So this is as I was mentioning at the beginning, this is a virtual reality immersive environment. So some of you may be familiar with the kind of virtual reality goggles that you wear. So you can wear some goggles on your head, and when you look into them, you appear to be in a 3D world. And those work quite well, but about 20% of people can't really stand wearing these things. They get nausea, motion sickness from wearing them. And also, they're really quite big, so they can hamper the kind of, they're big and heavy for a young child, so they can hamper the child's kind of natural types of interactions. So a way to get around that is to have a virtual reality environment in which we project things on the wall. So over here on the left is an immersive virtual reality environment in which the child is walking around in a 3D, so real world space, in which there are projections in all directions onto the floor and the walls, and the child is wearing kind of 3D goggles with some motion tracking on their hand and head as well. So the 3D goggles mean that, unlike us, who are only looking at this in 2 dimensions, they see and experience this as a real 3D world. And with the kind of motion tracking system and the motion tracking nodules there on their hand, the computer can keep track of exactly where the child is, how they're moving, and then update the scene so it moves in a natural way, in the same way as, when in the natural world, when we move our heads to the left, the scene appears to move to the right. And so we can do all that kind of relative movement stuff. So it really, I wish you could all come and experience it yourself. It really feels natural. And at the same time, within this natural environment, they can wear, again, our caps, which are recording brain activity. In this case, the little girl is wearing a functional near-infrared spectroscopy cap. So this is a system that measures brain oxygenation. It looks very impressive, but nothing is invasive. Nothing goes in. These are actually recording they're shining lights and recording how much light gets bounced back. And again, in the picture on the right, we see the little backpack at the back. All the wires go into the backpack, and there's a kind of wireless Wi-Fi emitter that transmits this data to the computer. So the child doesn't have to be plugged in. They can move around, run around freely, do anything they want. I mean, hopefully they don't roll around on the floor, but they can at least run around. And one of the examples of the studies that Chiara is doing is she's looking at children's kind of empathetic responses to different characters that they have more or less affinity to. So the children are introduced to a series of different characters, a man, a woman, a couple of children of different sexes, and a little toy or a fantasy animal as well. And they get to choose their favorite one. And then they play a game with that favorite avatar. And for example, on some occasion, they play an ice cream game, and the avatar's ice cream falls to the ground, and they have the option of doing something about it, like giving the avatar their ice cream or getting a new one for them, or not doing anything at all. And so their response to the person they like, or the avatar they have affinity to, is then compared to their response to an avatar that is randomly assigned to them. So again, this is to look at, first of all, the emergence of this altruistic, empathetic behavior, but also how it's modulated by the affinity of the child with particular character. So no results yet. And we're really looking forward to seeing how that turns out, because this is really absolutely a first time in the world that anyone has started to look at the emergence of this kind of empathetic behaviors in 2, 3, and 4-year-olds. So finally, just to come through a series of other studies that we're undertaking at the moment, this time in the preschool lab. This is a series of studies that's looking at neural synchrony during collaborative problem solving. And this is something I'm involved in, as well as my colleagues, Victoria St. Clair and Paolo Pinti. So it turns out that in adults, when we work effectively, collaboratively with each other, if we're recording neural activity, be it electrical or brain oxygenation, as we are interacting, if we're working collaboratively, effectively, we find that the neural signals are more coherent, more correlated than if we're not working collaboratively, or than if we're working, independently. And it's a little bit unclear why that is. But we started to look at the role of this neural synchrony in kind of early developments, in preschoolers in particular, but also, as you'll see, in primary school kids, but in preschoolers between 3 and 5 years of age, because this is the age when children transition from, say, parallel play to kind of playing together. So if you give some 3-year-olds some Lego, they will play Lego, but they'll do it in parallel next to each other. They'll each build their own tower or house. Whereas by 5 or 6 years of age, they'll work together to build a toy. And so we're interested in looking at the transition from this parallel to collaborative play, and what role neural synchrony might play in kind of supporting this collaborative problem solving in children of this age. So what do we mean by collaboration? Collaboration is basically working with someone towards accomplishing a shared goal. And there has been quite a lot of research in this kind of behaviorally anyway, in children in the age range I mentioned. We know it develops in the preschool years. It obviously involves interactions with others, and it's highly influenced by the interactive context that can kind of, the context that will either encourage children to work collaboratively or not. The takeaway message from that is that if you want to study collaborative learning, we really have to do it in real world type situations and contexts that the Toddler Lab offers, with multiple children, or at least 2 in the same place. As I mentioned before, in adults, there is evidence of kind of this neural synchrony during analogous, analogous brain regions during different types of collaborative tasks. So, I mean, it doesn't really matter what these regions are, but the important thing is different types of tasks illustrated at the bottom seem to show more synchrony in different brain regions, particularly the frontal type regions here, the frontal, which is involved in planning, executive control, attention, and then the TPJ in yellow here, which is involved in part of the temporal lobe and involved in kind of social cognition, judging other people's responses, mentalization, trying to understand what another person is doing, and then in the kind of lower temporal, inferior temporal regions, which is involved in knowledge retrieval as well. But there's no work on this developmentally at all, or very little. So we will be looking at neural synchrony using FNIRS, functional near-infrared spectroscopy. And I've mentioned that beforehand. I just want to make sure everyone knows what this is. This is basically measuring the blood oxygenation in parts of the brain in exactly the same way, or in a very similar way to what MRI is doing, fMRI, brain scanning that you've seen before. It's not really directly measuring the activity of the brain, but rather it's measuring the amount of oxygen that is available in certain parts of the brain. And the reasoning here is that parts of the brain that are working harder require more oxygen, which is the fuel, and therefore the bloodstream will bring oxygen to those parts. And we can use this kind of special infrared light to measure the amount of oxygen in different parts of the brain. So just to give you an example, a little video very briefly of the kind of task we have. So here we initially have a study which is looking at a 3-year-old interacting with their mother and collaborating to solve a 10-gram little problem. So this is very short, but it's just to show you behaviorally the kind of things that are going on. And at the same time, they're both wearing these caps. So we're measuring their kind of brain oxygenation, brain activity, different parts as they collaborate with each other. So there's no sound to this, but just to show you. So see, mum is kind of is cueing the child, ostensive cues about what to do, helping. There's joint eye gaze, and there are kind of pointing and verbal instructions. So lots of interactions going on. Now, one of the questions out there is what behaviorally is driving the emergence of this neural synchrony? And some people have argued that it was those ostensive cues that I pointed out, the joint eye gaze. So looking at each other is what causes the synchrony to occur. So in order to kind of tease all of this apart, we got mum and child here to kind of solve the problems under 3 different conditions. One here on the left, where they worked together with full cooperation. In the middle, they were allowed to collaborate, but there was a curtain hanging down, so they couldn't see each other's heads or faces. They could see their hands, and they could speak to each other, but they couldn't see each other's faces. So that was ruling out the eye gaze as a cue. And finally, over here, we had mum and child working independently with a curtain between them. And without going into long details, what we found so far is that, as has previously been shown, the experimental condition kind of predicted the level of coherence, of synchrony between the mum and her child. And that basically there was more neural synchrony when mum and child were collaborating, be it fully or be it with the screen half down so they couldn't see their faces. In both cases, collaborating led to neural synchrony between the mum and the child's brain, and not when they're working independently. And also, importantly, yes, okay, that's an interesting fact, there's neural synchrony, but what was important is that the level of neural synchrony between a particular dyad, between a mother and a child, significantly predicted how well they succeeded at solving the problems. So the strength of the synchrony was a predictor of how well the dyad had interacted with each other. And one of the big conclusions to draw away from that is that if we really want to understand what's happening in the brains of humans, we have to remember that humans are social animals and that we often work together. And so understanding functional neural systems, functional neural systems really needs to be understood in the context of the other brains that are around this child. Okay, so where are we going with this? So this was mum and child. What we're currently doing now is looking at this when children are interacting with each other. So this has never been done before. So we have a series of studies where Either these are siblings on the left, where a little 3-year-old is interacting with a 5-year-old's brother, I think, and they're working together to try to solve this problem. Either we'll look at siblings. We are looking at siblings or strangers. These are strangers, children that have never met before, or friends. They come in with their friends. And again, no one's looked at synchrony in child-child interactions. The final step into the wild, I think got another kind of 3 or 4 minutes of, the final step into the wild is that next year, once we figured out how this works in a more constrained system like this, we will actually have a group of 10 preschoolers, 5-year-olds, who are going to come into the preschool lab for 3 hours on a Saturday morning or afternoon for 3 months. And they will engage in a real preschool class experience with a teacher. And we will kind of record brain activity, synchrony, the emergence of synchrony between kind of dyads within that real classroom, to see how that emerges in the context of structured problem solving like this, but also in the context of kind of the natural problem solving that emerges in the classroom. So when the teacher says, all right, everyone, let's put the pencils away, you have to work collaboratively with your partner to make sure that that task gets completed properly. So watch this space. You have to have me back when I've actually completed that study. So I just want to very quickly, I appreciate that. Okay, I've got another 3 or 4 minutes, 5 minutes, I think. Okay, great. I'll keep going. So just to continue along this line of the synchrony between the mothers and their children, or two children together, the neural synchrony when they're working together. We have another project on the go at the moment, run by our PhD student, Becky Terry, in which she's looking at this mother-child interaction, but in the younger age group. So one of the reasons the ToddlerLab was built is that toddlers are considered to be the kind of black hole of developmental cognitive neuroscience research. We don't really know what's happening. We know quite a lot about brain and behavioral development in young babies because, I don't want to use the word placid, but they're happy to sit there and comply with our tasks. And we know a lot more about brain and behavioral development in older children because they will follow instructions. But that middle period, the kind of 2 to 3-year-old period, they just don't listen to what you tell them and they don't comply. So it's quite hard. Becky started her PhD a year and a half ago. And basically her project is to kind of see how we can adapt some of the methods that I was talking about before to this younger age group. And so she has an initial study, which I think we do have some preliminary results, which I think are really interesting, and show the benefits of doing this kind of research. So it's the same sort of thing. It's mother and child working collaboratively to solve a problem. In this case, they're building a Duplo house. And they either do it working together and we record brain activity to find synchrony, or they do it independently and they're separated by a curtains. And what she's found is a rather strange finding. So she did find that when they work together, there is a significant kind of synchrony or greater synchrony in the mother and child, and that's as predicted with the older age group. But she found that when they work independently, so this over here on the right, she also found a strong level of synchrony between a particular part of the mother's brain and the child's brain. And that's very surprising because, when you're working separately, doing different things, you shouldn't have synchronous activity. But in fact, the synchrony that she found was between what's called the TPJ, the temporal parietal junction in the mother. And this is an area that's involved in social cognition, in monitoring other people's intentions, and trying to second guess what they're going to do next. And the child's frontal cortex, which is problem solving. And what we've realized is that because these 2-year-olds are, they're 2-year-olds, they do need a little bit of help with the task. And we had a research assistant that was coming in. And if you just come back over here, the child wasn't always alone. The research assistant would come in and help the child out and would talk to them. And mom is sitting behind this curtain doing what is a really simple task for an adult and can hear what's going on the other side. And in fact, the reason her social cognition part of the brain is active is because she's more worried about how little Johnny is doing on the other side than about building this silly Lego house, right? In contrast, little Johnny doesn't, I hate to say this, isn't really focusing on mum. Little Johnny is focusing on solving the problem. So their frontal is highly active. So this we think is a marker of the parent and child or adult and child engaging in the task behaviorally, apparently in the same way, but actually through brain imaging, you can tell that they're engaging in a different way. Mum is engaging in it from a perspective of worrying about what her child is doing, or trying to second guess how her child is doing. Whereas the child is engaging in the task solely in the context of oh, I'm going to solve this fun game, and not really thinking or caring. I hate to use the word caring, but thinking about mum. And finally, just one final, yeah, that's exactly what I said. Just one final short sentence, because I know this is an educational audience as well. So we've also got a study with another PhD student called Imogen Green, who is looking at neural synchrony during classroom teaching. So it's not really classroom because we've got them in our preschool lab, but she's brought in actual teachers and kind of year 5 children, and the teachers deliver a bit of science curriculum. So they're teaching a science lesson, and we're looking at the neural synchrony between the child and the teacher as a function of the different types of teachings, of instructional styles. So we are comparing the synchrony that arises when the teacher is engaged in a more interactive scaffolding type of teaching activity versus a more explanatory kind of didactic telling the child about things. And then we are kind of looking at the immediate and long-term effect on the retention of the information. So does one of those teaching styles lead to better long-term retention? But more importantly, does the amount of synchrony that arises between the child and the teacher predict, in these different conditions, predict the long-term retention? Okay, and hopefully, if one does, then it gives us some evidence to provide advice to teachers in terms of the quality and the nature of the social interactions that are required to maximize kind of uptake of learning as well. Yeah, and so she also found a kind of association, increased synchrony between the child's frontal, where this is like they're working hard, focusing on the problem, and the child's TPJ, social cognition site. So the teacher is more engaged in trying to second guess the student's mental states, whereas the child is more focused on paying attention to the science material that they are trying to, being required to learn, and less on the social interaction with the teacher. Okay, so that's basically all I was going to say. I've got a cute slide to end with. So unleashing toddlers, they're not dangerous. They are fun, but they don't sit still and they don't listen to what you want them to do. We have many ongoing projects. I've just illustrated 4 of them: learning and sleep consolidation, learning and home distractions, learning to care, and neural synchrony and collaborative learning. There are several others. We'll keep you up to date. And that's it. Thank you very much for your attention and support. And we have down here several organizations that have kind of helped fund our research, and to whom we're very grateful.
Thank you so much, Denis. That was absolutely fascinating. It's a staggering piece of work to put this together in this way. I really appreciate how much has gone into this. When is it likely that you're going to be able to give us some results from this research?
What a good question. So, the scientific process is very slow. So some of these are actually more advanced than others. So I think the home noise, they already have some published results. And in fact, I would recommend you ask Natasha Kirkham to come in and speak to you. She's a great speaker as well. And some of the empathy work that I was talking about in the virtual reality cave is also kind of, the initial studies are finished and published and so forth.
Right.
So some of that's already out. There are a sequence of studies, of course, and so that will take a number of years. But I think the thing that people don't understand is that it usually from the beginning of a study to it coming out in press in a scientific journal or a more publicly accessible journal, there's usually about a 3-year lag. So it takes us a year to do it, a year to kind of analyze, finalize, and then a year for it to go through the publication process. So I'm often asked this question. It's far too slow, but there's not much we can do about it.
Okay. Yeah, just for my own interest, that last one about the difference between scaffolding
Mhm.
and the explanatory. Is there anything coming out of that?
Well, I mean, I think so oops, let me see if I can go backwards. So there are two things. One is you make discoveries by mistake. And I'm trying to hide you because it covers my slides. There we go. Okay, so you notice the curtain we have here. And so this came out of the previous studies. So a lot of previous work on neural synchrony was suggesting that it was joint eye gaze, the fact that we look at each other and we both jointly look at an object of shared attention that was driving the synchrony. And so we introduced the curtain to see if that was indeed the case. And so we would expect less synchrony when there's a curtain between the people. So one of the things that came out here is actually we had much stronger synchrony when there was a curtain than when there wasn't a curtain, which is quite surprising, particularly in the scaffolded region. Scaffolded type of teaching practice. But with hindsight, if you think about it, it's not really separating them. It's just making the task more difficult, right? I mean, they still need because the scaffolding to have social interaction. We've just made it harder, so they are working harder, which is probably why they're paying attention more and so forth, which is why there's an increase. So that's an element that is less relevant to teaching per se, but was more relevant to our understanding of the basic mechanisms.
Okay, thank you. Ellie Willard has a question here. That was really interesting. Thank you.
Right.
I was teaching about brain synchrony and learning a couple of weeks ago. I just wondered, how long does it take toddlers to get used to their headgear? Are you able to tell when they are no longer aware of it so that you know that the brain activity is not affected by it?
What an excellent question. So actually, it's pretty quick, and it kind of depends on it kind of depends on what else is going on. When we do the studies in the virtual reality caves, that is so much fun. Okay, that within like 3 minutes they don't care about the cap and they're really engaged in the task. If your task is a little bit boring, which in the kind of home distraction, home noise stuff is. The problem is that the caps they have to be quite tight, so they really do feel a bit like a swimming cap. And if you wear it for a long time, it gets uncomfortable. So I'd say about more than half an hour for the kids, 45 minutes, it gets uncomfortable. Right. So, young preschoolers and toddlers get increasingly fidgety and disruptive, and frankly, we'll just say, I'm not wearing this, take it off. But that's depends on how interesting the other stuff is. But that's a really great question.
Okay. Toby Whitaker says, thanks for a really interesting presentation. I was wondering if there are any other measurement technologies you've used in the lab or are considering using going forward.
Another difficult question. I mean, no, it's a good question. There's a lot of different measurement technologies in terms of I guess there's lots of things we could be measuring. One of the things we've used previously, but this is more like motion capture. I talked about motion capture. You can use EMG, so electromyographic myography, and that's basically measuring the electrical activity in muscles. So you may or may not know that muscles basically function on the basis of an electrical signal. So when my arm moves, my bicep contracts, and it does so because an electrical pulse has gone through it. And you can measure those electrical pulses in preparation for a movement, even if the person doesn't carry out the movement. It's another kind of window into their intentions. And so we in fact have done this as well. You can look at empathy and emotion judgments. So we have a tendency to mimic the emotions of the people, especially the very strong emotions of the people in front of us. So laughing is contagious. If someone is really happy and smiling, you have a tendency to micro smile. Or if they're really sad, you have a tendency to kind of have a sad facial expression, but it doesn't always come out, right? I mean, we're able to control ourselves, but you can see those movements, those smiles, for example, being prepared if you record the muscle activity on the face.
Right.
So we've kind of been using that to look at babies and toddlers' understanding of others' emotions and empathy. So at what point do they start to mimic the emotions and of a participant or a character that they're seeing? So yeah, EMG, wireless EMG we use as well.
Right.
There are, but you know what? This is brand new. We have way too much
Yeah.
technology. Not too much, but there is a lot of it.
Yeah.
So I
Yeah.
don't add too much in.
I thought the thing about the motion, monitoring the motion and the micro movements that people make, that's absolutely fascinating, because it's not something that would ever have occurred to me, as part of the scenario. But yeah, that's absolutely brilliant. I don't. Does anybody else have any more questions for Denis?
I can maybe, if you don't, I can maybe just follow up on something, or just to say. So people, you sorry, do you mind?
Go on.
I'm saying, if you I'm just looking at the time. Our aim here is to capture natural behavior, right?
Right.
But if you look at the pictures, I think you can see the pictures of the kids here. We already have quite a lot of kits on them. So these children are wearing this cap, and they're also wearing, you can't quite see it, but they're also wearing the wearable eye trackers.
Yeah.
I was looking for one. Where is it going to be? I think back here. Here we are. I mean, she's wearing the 3D glasses,
Yeah.
the cap, and they often wear motion tracking gloves, like here as well. And they're starting to look a bit like cyborgs.
Yeah.
And a criticism or a comment that's been made is the extent to which this is really, naturalistic behavior. So it's one thing for the child by themselves, interacting with an avatar. But if we're looking at here we are, kind of real social interactions,
Yeah.
I mean, if it's siblings, yes. If it's strangers, it's a bit of a weird environment, right? So I think there's this compromise between having more technology, which allows us to measure more things simultaneously, which will give us a richer understanding of what's going on, while at the same time trying to keep it somewhat real.
Yeah.
Yeah.
Yeah. So this stuff doesn't get in the way too much.
Exactly, and not physically in the way, because this stuff actually weighs, it's not that heavy.
Yeah.
It's not natural, but also in terms of, you're really interested in natural social interactions, in terms of kind of changing the child's interactions.
Yeah.
If you don't know, if these two children don't know each other, it's harder to make friends, as it were, when you're wearing this weird stuff than when you're, at the park.
Yes, I completely understand that. Well, thank you so much, Denis. That's been absolutely fascinating. And I'm sure if people do have any more questions, then we can forward them to you.
Absolutely.
And please remember that the video will be on the website shortly and on our YouTube channel. So just to say thank you so much, Denis, yet again, for a really, really interesting presentation. And thanks for joining us this afternoon.
Great. Thank you very much.